Welcome to this comprehensive 10-minute masterclass on Z electrostatics. We begin our journey with the foundation of it all, Coulomb's law. In 1785, Charles Augustin de Coulomb discovered that the electrostatic force between two stationary point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Mathematically, F equals kq1 q2 over r squared. Notice in this 3D visualization how the force vectors change as we manipulate the charges. If both charges are positive, the vectors point away from each other. This is repulsion. If one is negative, they point toward each other, attraction. As we increase the distance, the force drops off incredibly fast. This is the famous inverse square law. In the Z exam, you will often encounter the principle of superposition. This means that if multiple charges are present, the net force on any single charge is the vector sum of all individual forces. Watch as we add a third charge to the system. The complex interplay of vectors shows why vector addition is a critical skill for this chapter. We will now spend a moment observing how the force field behaves in 3 dimensions around these point charges. Moving forward, we transition from forces to the concept of the electric field. Michael Faraday introduced the idea that a charge doesn't just push other charges, it modifies the space around it. The electric field E is defined as the force per unit charge. Visualize a single positive charge. It radiates field lines outwards in every direction, filling the 3D volume. Now, look at the electric dipole, a pair of equal and opposite charges. The field lines emerge from the positive and terminate on the negative charge. In Z Advanced, you'll need to calculate fields for continuous charge distributions. Observe this infinite line of charge. The field lines extend radially outwards, perpendicular to the wire. Next, look at the infinite plane sheet. Here, the field is remarkably uniform, it doesn't decrease with distance. Finally, observe the electric field of a charged ring along its axis. At the center, the field is zero due to symmetry, but as we move along the axis, it reaches a maximum before eventually fading away. Understanding these 3D patterns is essential for mastering the next topic, flux. We now arrive at Module 3, Gauss's law, perhaps the most elegant tool in electrostatics. Gauss's law states that the total electric flux through any closed surface is equal to the net charge enclosed divided by the permittivity of free space. Flux is essentially a measure of how many field lines pierce a given surface. Watch as we place a charge inside a sphere. This is a Gaussian surface. Because of the symmetry, the field is perpendicular to every point on the surface, making calculations simple. But Gauss's law works for any shape. Even if we deform the sphere into a cube, the total flux remains the same, provided the charge stays inside. In Z, we use Gauss's law to find fields that would otherwise require complex integration. Look at the hollow conducting sphere. Inside, there is no enclosed charge, so the electric field is zero. This is the principle behind electrostatic shielding. Now look at a solid non-conducting sphere with uniform charge. Inside, the field increases linearly with distance from the center. These visualizations show the power of symmetry in physics. Module 4 focuses on electrostatic potential and energy. Just as a ball has gravitational potential energy when lifted, a charge has electrostatic potential energy in a field. Potential is a scalar quantity, which makes it much easier to work with than vectors. In this 3D view, we see equipotential surfaces. These are regions where the potential is the same everywhere. For a point charge, these are concentric shells. If you move a charge along these shells, you do no work. Notice the relationship between field lines and potential. Field lines always point from higher potential to lower potential, and they are always perpendicular to equipotential surfaces. Look at the potential landscape of two like charges. It looks like two hills. A positive charge would roll down these hills. In Z problems, remember that the work done by an external force is the change in potential energy. We also visualize the potential of a dipole. It has a zero potential plane exactly in the middle. Mastering the transition between the scalar potential and the vector field is a hallmark of a top Z student. Finally, we conclude with capacitance and the storage of electrical energy. A capacitor is a device used to store charge and energy. The most common type is the parallel plate capacitor. When we apply a voltage, one plate becomes positive and the other negative. Inside the gap, a uniform electric field is established. Look at the energy density within this field. If we insert a dielectric material between the plates, notice how the field within the dielectric is reduced due to polarization, which actually increases the capacitance. In Z advanced, you will often see complex circuits with capacitors in series and parallel. Remember, the energy stored is half CV squared. Visualize the charging process. As work is done to move charges onto the plates, the electric field grows, storing that work as potential energy. We also look at spherical and cylindrical capacitors. This concludes our 10-minute masterclass. Use these 3D visualizations to build an intuitive map of electrostatics in your mind. Practice the problems, visualize the fields, and you will excel in the Z exam. Good luck.